Nadia how. My name is Genady, and I'm from I-Photonics company. That is a company that manufacturing and developing vacuum coating systems for silicon technologies. So technically, we are mostly optical coating company, but we are moving forward to integrate our experience to semiconductor field, to silicon photonics, etc. And the company is actually very young, but people in our company have experienced like 10, 30 years in this field. Today I will present our related recent work on LED passivation using high-density plasma reactive magnetron sputtering. And specifically, I will be talking about some very, very tiny invisible layer that needed for LED to guarantee its durability in aggressive environments. And anyways, need to explain about our company a little bit. We have three branches of business, and the main one is vacuum coating system development and production. And we have some standard portfolio of coaters that have very different coating techniques. And different coating techniques like evaporation or sputtering are required for different applications, for different wavelengths, for example, for laser coatings, for hardening coatings, etc. And also coaters might have different productivity, like batch coater, R&D coater, or industrial scale coater. So the variety is quite big. And we have R&D department. It's my favorite part, where we focusing on solving some challenging tasks from our customers, from our partners, how to apply certain material to another material, to another substrate, to another substrate with different shapes, to guarantee some specific optical spectrum or mechanical properties, etc. And the last one is optical components production. So we have the set of our standard coaters back in Lithuania, in Vilnius, where we can make some test samples or produce some coatings for our customers. And coatings could be very different. Could be filters, mirrors, anti-reflection coatings, hydrophobic coatings, hardening coatings for wide wavelength range from UV to far infrared, and could be applied for different materials and shapes of substrate. And from this slide, you can see our presence in the world, and especially I want to focus for Taiwan. And here in Taiwan, we have constantly located team of engineers and manager. So, and we give some support to our customers in Southeast Asia. And actually, I'm very grateful to be here because Southeast Asia is very warm and people are very kind. So, and let's go back to the technical part of my presentation, and we're talking about LED passivation. So let's start from why. Why do we need some additional passivation for LED when each LED is actually encapsulated already? It has some capsule made of silicons, made of epoxy, that can guarantee its protection from some mechanical stress, mechanical damage, or water, etc. Any short-term impact. So, but here's why. Because of application. Some LEDs should be used for a long time. For example, in our cars, in some industrial lights, where the lifetime required is like 10, 15 years or more. And for LED, it's quite a long time, especially in environment that is quite aggressive and containing corrosive gases like hydrogen sulfide or hydrogen oxide, etc. And here, when we need a long lifetime, we come to the situation when encapsulation cannot guarantee the protection, because in long term, we need to consider slow processes like diffusion. And in long term, encapsulation becomes transparent, actually transparent for small molecules like hydrogen sulfide or hydrogen oxide, and through the time it can diffuse through encapsulation and react with, for example, silver reflector layer. And silver reacts very well with hydrogen sulfide, for example, forming not bright mirror, but yellow or brown or dark layer. That is, first of all, changes the color of LED, and second is a reduction of light intensity coming from LED. So light intensity could be decreased by like 50% at least. That is not a good condition. So that's why additional sealing layer is required for LED for automotive application or for some industrial applications. So this layer should reduce the diffusion of molecules to silver. And also this layer should not interfere with the optical performance of a light emitting diode, and also keep not damage the electrical performance. So here, silicon dioxide is a quite good candidate. And you might think, okay, Genady, you have so much coating equipment at your facility, you can apply silicon dioxide by so many methods, so why not just apply? Okay, but because we are an optical company, we know that silicon dioxide could be very different. It could be porous, it could be dense, it could be crystalline, it could be amorphous, it could make some pillars or make some nanoballs on the surface. And we need exact film structure to guarantee the passivation. And to verify the passivation quality is very new standard made in 2020, AEC Q102. So the test passivation quality focusing on the most frequent failure mechanisms such as silver oxidation. So, and another challenges first is that LED surface is not flat, is developed. It has some vertical walls, wire bonds, some steps, and the passivation coating should be applied over all this structure. Despite of shadowing effect is when some areas of the substrate can have from little to no any coating. In this case, it will be damaged through environmental stress test. And also, such film that has good conformity and high density should be applied in regimes that will not damage the silver layer or PM junction, etc., without overheating and damaging LED itself. That is also quite challenging. So, and considering all these challenges, potential issues, and also very important the productivity, because we also challenge to make the process that comparable to some PVD processes by price and the productivity itself, and balance it with a good quality that follows the required standard. So, and what is the solution? We came up with two-step deposition of single silicon dioxide layer. So, first step is silicon dioxide sputtered in soft regimes when oxygen energy is too low to react with silver, and ion bombardment is also too low to damage semiconductor structure or other stuffs. So then, after the soft barrier layer, soft buffer layer, we are going to apply the barrier layer of high density. And for deposition of such barrier layer, we need to use more aggressive regimes that by itself can damage the LED. But such aggressive regimes will make sputtered atoms to distribute over the developed structure of LED and increase the density of the coating. So, and technically this barrier layer is responsible for protecting LED from the stress test. And talking simply in this concept, buffer silicon dioxide protects LED from deposition of barrier silicon dioxide, and barrier silicon dioxide protects LED from environmental stress test. So, and both times silicon dioxide was sputtered using AC twin magnetron in a reactive magnetron sputtering process, but for the second step, it was additionally assisted by inductive coupled plasma that increased the plasma density, increased mobility of sputtered atoms to densify the field. So, first step by standard reactive magnetron sputtering, and second step by high density plasma reactive magnetron sputtering. So that is the topic of today's presentation. And here we are. Here is the result. We passivated many LEDs with different approaches and measured the light intensity before environmental stress test and after stress test. So the stress test was conducted during 336 hours with silicon oil, hydrogen sulfide environment and high humidity. And so vertical axis shows how degradation of optical properties were reduced, or how optical retention was improved after some steps of deposition. So, and left graph shows that very logical fact that increasing the thickness of barrier layer of silicon dioxide, keep a constant buffer layer of 5 nanometers, the flux retention, it means the light intensity was flux intensity improvement was increased when we increase the layer thickness. So it means that hydrogen sulfide actually see that it sees the barrier layer as a problem, so it cannot just diffuse through. If you use just normal sputtered silicon dioxide, that doesn't matter. So if the porous layer, if it have 40 nanometer or 100 nanometer, it will not pass and it will cause the same result after 336 hours. But if the layer is dense and it really affects the diffusion, increases the diffusion path, so the efficiency is increasing. And from the right side, it shows how optical retention was improved while we balancing the ratio between buffer layer and barrier layer, keeping constant total thickness. So it's a classic balancing task and balance between process-induced damage of LED and coating quality. So from right side is completely soft silicon dioxide. It doesn't pass environmental stress test. From left side is 100% dense silicon dioxide. In this case, LED was destroyed even already after the coating. So, and the good result is somewhere in between soft layer and dense layer. Okay, and here is as a conclusion. We tested two-step approach of LED passivation, including reactive magnetron sputtering in standard regimes and high-density plasma regimes. Our results showed that they cannot work separately, so it will not pass environmental stress test, or LED will fail immediately after the coating. But combining standard reactive magnetron sputtering with high-density plasma reactive magnetron sputtering, we achieved some improvement. It's at least 25 improvement in resilience or retention of optical properties of LED, and most of AEC Q102 parameters passed the test. And improvement in sealing properties, yes, is caused by using high-density plasma, because it makes silicon dioxide layer more dense, and diffusion barrier was crucial for hydrogen sulfide to oxidize the silver. So, and finally, that high-density plasma reactive magnetron sputtering almost reached the parameters of standard, and being very scalable, it is a good balance between standard PVD methods and atomic layer deposition method. As you know, atomic layer deposition is a quite good conformal method of coating, but it takes a lot of time and a lot of price. For example, for such coating, high-density plasma reactive magnetron sputtering is around 3 minutes process, but for ALD it's around 2 hours plus minus. So it's like a lot beneficial. And this method, reactive magnetron sputtering, is also becomes very scalable. And actually now we are moving forward to integrate this process to mass production. First of all, to improve the initial quality of LEDs that we have, LED substrates. Because when we work with LEDs and the customer send this to us, it's already partially oxidized. And we are going to integrate our system to mass production system and move forward to meet all the requirements. Okay, thank you. Here is the last slide when you actually see our headquarters in Lithuania, Vilnius. So when we do our research and development work, when we produce vacuum coating equipment and vacuum and coated optical components. So of course, yeah, the most interesting part is inside, and we love to invite our partners, our customers to our facility to discuss how can we collaborate, to show how our equipment work, to make some demo samples for our customers, etc. And of course, to show our beautiful city with long history to our customers. And, yeah. So you're welcome to see it yourself. Thank you.